Okay, so here's where we were last time. We were talking about this, I think, very surprising result about determinant. Look, by the way, quick reminder. Here's how we define 2x2 determinants. Notice four-function arithmetic, very simple formula. Sort of eyebrow-raising minus sign here, I suppose, right? But other than that, seemingly harmless, seemingly uninteresting. But look at this wacky theorem. If you take a couple of vectors, take the first one, draw it, make it the first row of a matrix. Take the second one, draw it, make it the second row of a matrix. The area of the parallelogram will always be equal to the magnitude of the determinant. This is super weird. I mean, who saw area coming from that formula? Right? It's does not leap off the page at you, does it? Right? And arguably even more sort of mysterious, the order, whether, AB is a clockwise or counterclockwise order. Critically, of course, you've got to make sure to make the vectors, the rows, in the same order that you're interested in. The sign of the determinant tells you about the order. This is very, very surprising. A tremendous amount of geometric information in this seemingly unimpressive, uninteresting little formula. So crazy weird. Okay, what about this, the 3x3 case? That's where we left off last time. Well, in the 3x3 case, it's surprisingly similar. So now with three vectors in R3, first vector, first row of the matrix, second vector, second row of the matrix, third vector, third row of the matrix. And again, determinant in some sense tells all, right? So the determinant of the matrix by its absolute value tells you the volume of the parallelepiped. So again, who saw volume coming out of this? I emphasize, this is not a rectangular box we're talking about here, right? This thing here has got all sorts of weird angles on it and stuff. Wouldn't you think that there'd be trig involved to compute that volume? But there's not. It's the absolute value of the determinant. Very strange. And again, also mysteriously, the order that you wrote these down, the handedness of that order, again, critically assuming that you make them the rows of the matrix in the same order that you wrote them down in the first place, that handedness is entirely decided upon by the sign of the determinant. Right? Really weird. So positive means right-hand order, negative means left-hand order. I think that's very mysterious. I'm not going to prove these two results for you. There's different ways to prove these results. By the way, there's many different ways to go through and present and connect the ideas that we're talking about here in this section of the book. Some of them are more rigorous. Some of them are more intuitive. Some of them are more geometric. Some are more algebraic. There's a million different ways and a million different pros and cons, right? So I've selected an ordering pass through the idea that pros and cons, it's a little bit less rigorous because I'm not going to prove these results. But there's a great way to prove these results. It's just a little too sophisticated for us to talk about here in Math 212. If you're curious, you can come to my office hours. I'm happy to talk to you about it. Or you can wait until you take a linear algebra course, in which case it'll be more accessible. But with that one little the order that I'm going to take through these ideas will be heavily geometric and heavily intuitive, and I think it's worth it. In a class like Math 212, I think that's the right sacrifice. So anyway, okay, so not going to prove this result. Okay, a quick example like we saw with the two-dimensional case. Here's a trio of vectors. Now, let me point out in 2 dimensions, it's easy to say, come on, I can just draw the picture of the vectors, and arc tangent's going to tell me the angle, and the angle between them is easy. these three vectors, it's actually pretty hard to tell, wait a minute, are they like this or are they like that? And which way do they really, is this a right-hand order or is this a left-hand order? It's not obvious when you're in three dimensions. And there's no sort of like, oh, I'll just fall back on trig sort of approach that you can take. Right? So how do you decide? Well, nice answer. We follow the rule. We take these vectors, make them the rows of the matrix, right? Compute the determinant. The magnitude of 21 gives us that volume. The volume of that wacky parallelepiped. No trig necessary. And the fact that this is positive tells me that this is a right-hand ordering that I've written them down in. Positive means right-hand order. Yep.
What's the benefit of determining whether it's a right-hand order or a left-hand order?
It's more so that it's just so weird that the sign of the determinant means anything geometric at all, right? And then now there are some situations, and so if you talk about applications to physics and stuff, how to if you have an electron, a charged particle moving through an electric or moving through a magnetic field, the way the corresponding forces is, it depends on handedness. Right, so there are physical applications, and that's too much of a digression for me to go into the details. But there are circumstances where it matters. Yeah, right. I have a vague memory. Here's an unprepared example to answer your question. I have a vague memory from when I took an organic chemistry class. Oh golly, so many years ago. I don't want to make that too precise. But apparently, there are some chemicals in the human body that are essential for life, where the handedness of the way the bonds fit together, how this connects to that, and whether it's this handedness or that handedness, makes them react chemically in different ways. Somebody probably knows more about this than probably most of you know more about this than I do. So that's an example. Weirdly, if you were, somehow, transformed by magic to be a mirror image of yourself, every single particle in you were mirror imaged, you couldn't survive in this universe because the chemicals that you need with that chirality, is that the word? I think it's chirality, would be wrong, and so you'd die. Which is horrifying, but interesting. Yeah.
Wait, but when you do the handed rule on, or the rule on that, so wouldn't the thumb point to the other side?
So, okay, what this is saying is, and by the way, I don't know if my picture is entirely accurate, but so here's the first vector that looks like that one, and then here's my second vector that looks like that one, and here's the third vector that looks like that one. So, first, second, third, right-handed. Yeah, right. As is indicated. So the right-handedness of that, if you will, is clued in by the positive of the determinant. Yep. Okay, so we've talked about a bunch of stuff that are not cross products. We talked about handedness, we talked about determinants, we talked about the geometry of those things, and all of this in a section whose really primary goal is for us to talk about cross products. So let's actually go ahead and do that now. Here's our definition of cross product. It's a formula that I write down, pull out of thin air with apologies, right? I mean, normally it's nice if we can write down a formula motivated, right? Like we did for vector addition. But it turns out to be an awkward way to do cross products. So anyway, so I am going to give you a geometric motivation for this. In some sense, the rest of this section is to motivate geometric intuition about this weirdo formula. But I'm going to start out by just writing it down. Before we go on, good news. Notice that a vector and another vector cross product to produce a vector. That's a relief compared to dot products, where two things you multiply and you get a completely different kind of critter, that which was weird, right? So this is a little bit more natural in that sense. Bad news. This is only for vectors in R3. We're not going to talk about any sort of a cross product in R2 or cross product in R7. Nothing but 3. Now, quick asterisk. There is a construction in other dimensions that has a lot of the features of cross product, and it's very neat, but it's not really a product. This other construction is not what we call a binary operation, where you give me two things and out comes another thing, right? So this is what we call a binary operation. And I think of products as being binary operations. So these other higher dimensional cross products are not products. And so in fact we don't even really call them cross products. Okay, that was an asterisk. Okay, so we have a formula. Given a formula, we can start writing down algebraic properties. This is where most people kind of like their eyes glaze over. Yeah, of course. I yawn, right? These things, anything that looks like it ought to be true, anything that looks vaguely familiar from, elementary school, commutativity, associativity, distribute, all those things. Come on, surely it's true. Here's our first easy example of no, it's not. V cross W is not equal to W cross V. But it's weirder than that. Not only are they not equal to each other, they are always exact negatives of each other. So that's an eyebrow raiser, right? Like, whoa, what's going on there? Okay. This one looks pretty satisfying. This seems to suggest, well, it's kind of like a sort of a associativity kind of sorts that involve dot products and cross products, but it kind of looks like you can do the times in whatever order, seemingly. What's weird about this one is notice that there are 6 different ways that you can order 3 vectors, and I've only written down 3 of those 6. So what's the deal with the other 3? And are they all equal? And, well, no, they're not. So just keep that in mind. It's not hard to see why. So, for example, on that list, we do not have V dot U cross W. This is not equal to those other things. And in some sense, well, of course it's not, because we know that these two things are negatives of each other. Right? So therefore, these two vectors being negatives of each other means that these two values are negatives of each other. So they're not equal. Okay. All right. Okay. Also, neat fact, easily proved algebraically, but there's geometric intuition that we'll talk about later. If a cross product is the 0 vector, that means the two vectors are parallel, or one of them's the 0 vector, or both of them are the 0 vector, and there's this little sort of, non-zero asterisk that you have to throw in there. Another way to say it, and a little bit more elegantly, kind of sort of a cross-product version of the orthogonality word that we came up with, is that when the cross product is equal to 0, one of the vectors is a multiple of the others. And it's not hard to persuade yourself this is equivalent to saying one of the vectors is a multiple of the other. Okay, so all of these can be checked algebraically. Just punch it up. It works, right? I emphasize my own view anyway is that when you prove something and it's just cranking algebra, it's rigorous and unsatisfying, right? So a lot of what we're going to do over the next few pages is not try to talk about which facts are true, but to try to develop some satisfying sense of why should they be true. Right? So why should this be the case? All right? Stuff like that. Okay. So I'm going to try to emphasize intuition. Okay. Another fact. Now again, this can be punched up algebraically. Direct calculation. The cross product is always orthogonal to each of the 2 input vectors. Right? When you cross 2 vectors, V and W, you'll be perpendicular to V and perpendicular to W. Or 0. Okay. So neat fact. Now, how do we know this is true? Well, don't forget orthogonality is easy to check. Orthogonal means dot product is equal to 0. So if you want to confirm that V cross W is orthogonal to V, you just punch up that dot product. This is a pretty easy calculation, by the way. I think everyone should do this once in their lives. It'll take you about 30 seconds. Write down the formula for the cross product. write down the formula for the dot product, crank it out. There's 6 terms. They all cancel mysteriously. And it's just kind of nice how that works out. Okay. Likewise for W. Okay. So again, what I've done here is I've given you an algebraic, irrefutable. I mean, the dot product's clearly 0, and yet somehow still pretty unsatisfying claim here. So I can see that the cross product is always orthogonal to V, but I'm left wondering, why should it be orthogonal to V? So keep in mind, we're gonna try to straighten that out. Okay, there's another situation here where I have to do a little bit more algebra. This is algebra that allows us to make a nice connection that's going to make everything else in some sense streamlined from here on out. And so firstly, I'm going to observe that here's an alternative way to write the cross product. Let me sort of tell you where this comes from. You look at the formula for the cross product here, and notice that first coordinate looks just like a 2x2 determinant, doesn't it? It's like AD minus BC, but with different variables. Likewise, that looks just like a 2x2 determinant. Or if I were to take the negative of that, hypothetically, it would still look just like a 2x2 determinant. And likewise there. So we observe that the coordinates are all 2x2 determinants. And really that's all this says. This says V cross W. By the way, here are the coordinates of that vector that I just wrote down. Keep in mind, the coordinates are the coefficients and a linear combination of the standard basis vectors, right? So A comma B comma C is AE1 plus BE2 plus CE3. So all I'm doing is rewriting the coordinates here as determinants. I will call your attention to the fact that mysteriously I've written down this second coordinate as a negative of a determinant. Now still true, right? If I were to take the negative of this, it still looks like a 2x2 determinant. Seems odd to throw in an unnecessary minus sign. I'll grant you that. But look what good fortune befalls us if we do it that way. And that is, now, not only are the coordinates looking like determinants, but in fact, this whole thing looks like a 3x3 determinant. And again, weirdly, in order for it to have a 3x3 determinant, you do need to have that minus sign there. So that's why I did that. Okay, now I want to address a discomfort that you may be feeling. Here I call this a determinant. We talk about determinants of matrices. Okay, wait a minute, but is this a matrix? Are you allowed to have elements of matrices be something other than numbers? You've probably never seen a matrix where the entries were anything other than numbers. Can you just put anything in there you want? Can I make an entry of a matrix a bicycle? Is that allowed? Is that cool? Is weird matrix, maybe? Is that okay? So there's some uncomfortable questions that come up as a consequence of the fact that that is not a number. That's a vector. And we don't really need to dive into that. So what I'm going to say is I'm going to basically dodge the question and say, let's not worry about whether this is mathematically allowed, but let me just observe that if I say, let's take just a symbolic point of view, think of what I've written down here as just a, ignore what these things actually are, follow the symbolic rule for how to compute determinant, and notice that this gives you exactly what I wanted it to give me. Okay, so I'm just going to call this a symbolic determinant. Okay. Next fact I want to point out, and this is the really important one. Before I get to that, I encourage you all to memorize this formula. It's a really good one to memorize. And the reason why is, notice that it's a formula for the cross product. Wait a second, we already had a formula for the cross product. Why don't I just memorize this formula for the cross product? And answer, I think this formula for the cross product is really hard to memorize. You're going to find yourself at some point tearing your hair out on an exam trying to remember, oh God, is that third coordinate, is it V2W1 minus V1W2, or is it V1W2 minus V2W1? Which way does it go? One of them's right, one of them's wrong. They're off by a minus sign. I can't remember which one it is. Right? I mean, it's going to be hard to remember that. On the other hand, this formula here, super easy to remember. we put the standard basis vectors across the top row, then that vector, and then that vector in the same order that we have them listed, right? So first, second, third. It's pretty straight up easy to memorize. Now, of course, now you have to compute a determinant. Yes, you have to have already memorized the formula for determinant, but you had to do that anyway, right? So as long as you've already done that part of the job, then this is, I think, basically a freebie. So in my entire life, I have never memorized this formula. Ever. Not even when I was a student. Right? I saw this formula and very quickly decided, oh, well, that's the one I'm going to be able to remember. Boom. Okay, that's just advice. You're welcome to memorize the other one if you'd like. Suit yourself. Okay, next fact. Next important fact. This one's a little weird. Very weird. We've been talking about this cross product. Notice this next formula is not telling me the cross product. It's telling me how to do a dot product with this cross product. Okay, let me do that here for you, if you will. I'm going to take a vector u, and I'm going to dot it with this cross product up here. Now, how do you dot product with something? Well, the way you dot product is you take the coordinates of the one vector, here are the coordinates of that yellow vector, and then you multiply by the corresponding coordinates of the other vector. I'm deliberately writing this right on top of there. Right? So, a dot product is the sum of the products of the corresponding coordinates. That's all I've written down there is what's the dot product. And now notice that what we have here, just like what I just got through trampling, looks like a determinant. Well, so does that. That's still, it's the exact same thing. So therefore that is a 3x3 determinant also. It's the same observation. Okay, so neat fact. Let me clean up my mess here. This construction, a dot product with a cross product, is computed by a determinant. This ends up being a really big deal. It's going to be super useful for us. By the way, this is so useful, this construction being, my gosh, it's a determinant, is such an important fact that we give this a name. This is called a triple product. That's just the word that they use for it. So a dot product with a cross product, called a triple product. So the way to describe this equation then, and we're going to be doing the following quite a bit, is to say triple products are determinants. So you're going to hear me saying very often triple products are determinants. There it is. It's just algebra. Okay. The reason, there are many reasons. In some sense, the intuition for why this formula should be useful, for why you should be thinking, oh yeah, I can see how this is going to be good, is as follows. We already understand dot products geometrically, right? Pretty well. We know a lot of geometric information about dot products. We understand determinants pretty well geometrically. I have then here a formula that relates the construction I'm trying to understand geometrically with constructions I already understand geometrically. And so there's a foot in the door, right? This is how we're going to understand cross products better. Okay. So here's my first example. Let's go back to our already established fact. We already know that the cross product is perpendicular to the two input vectors. Yeah. Right, we crank it out. Just do the dot product. There's 6 terms. They all cancel. You get 0. It's easy algebra, and yet it's algebra, and therefore kind of, leaves you a little empty, right? So where's that satisfaction? Why should this be orthogonal? I want to ask, right? And I think the following is a pretty good answer to why it should be. Orthogonality is determined by dot product. We've already sort of done that. But wait a second. This dot product is, you'll notice, a triple product. Triple products are determinants. And determinants are volumes. Right? So we've now, this is weird, but we have just connected orthogonality to volume. in this little scenario that we've constructed, right? And what can I say about the volume here? Well, don't forget what we're talking about is the volume of the parallelepiped that I get when I take the first vector, v. Now the second vector, weird, also v. And then my third vector, w. Right? How much volume is there in this corresponding parallelepiped? I emphasize a parallelepiped. Right? Here's three vectors defining a parallelepiped. There's a parallelepiped, two of the vectors of which are parallel. It's like instead of having a box, it's like I have, this box has been squished for recycling. How much volume is there inside of a box that's been squished for recycling? Well, kind of the point is none, right? That's why we recycle them squished, so they won't take up a bunch of space. So there you go. That's the idea. The volume is 0 for visually obvious reasons. I'm going to say visually obvious that this volume is 0. Well, if the volume is 0, that means the determinant is 0. That means that the triple product is 0. That means that the dot product is 0, and dot product equals 0 means orthogonal. So there's some geometric satisfaction to be had in thinking about this question this way. I think much more than, crank out the dot product, do the algebra, answer indisputable, right? And again, it's indisputable and yet unsatisfying. Okay. All right. So there's a lot to digest. I hope you'll take some time, eye it up, think about it, let the ideas sink in. It's a great exercise also in using features that we've now learned about cross products and determinants and dot products. And there's a bunch of ideas that connect together here in unusual ways to give us an interesting point of view on something. Got to let that sink in, and it takes time. Did I see a hand somewhere earlier? Yes.
I did.
Yes.
So why are you choosing to dot product it by v?
So I'm addressing here the question of is that orthogonal to that, and that is done by that. Now you're quite right that if I wanted to consider the separate question of is it orthogonal to w, well then I'd have to dot it with w, and all I'd get then is still two of the vectors are the same, but instead of being this, it'd be like that. So, but yeah, morally equivalent. Yeah, right. So. Details of that calculation, why is v cross w orthogonal to w? Take out a clean sheet of paper at some point in the near future and see if you can write out that argument on your own. It'd be a good little practice exercise. Okay. Great question. Thank you for that. Okay. Next question. What's the deal with this one? Now, again, you can crank out the algebra, and it's indisputably the case that these formulas, when you crank, they are the same formulas, all the same 6 terms, and this is clearly true. But why should it be true? Where's the satisfaction? Satisfaction is as follows. These are 3 triple products. Triple products are determinants. Well, wait a second. Well, determinants relate to volumes and handedness. Right? And notice these 3 triple products, aka determinants, related therefore to parallelepipeds, they all have the same 3 vectors in them. Therefore, they're the same parallelepiped and therefore the same volume. They're also cyclings in terms of the order, and therefore they all have the same handedness, and therefore the determinants all have the same sign. So these parallelepipeds, geometrically, geometrically we're talking about this again, right? It's the same 3 vectors with the same handedness, just instead of 1, 2, 3, I'm doing 3, 1, 2. It's the same parallelepiped, same order, same handedness, therefore same determinant, therefore same triple product, and therefore, as desired, these 3 things are the same. Geometrically natural. There's ideas that you can visualize in there. So I find that satisfying. and if nothing else, also easy to remember, right? As opposed to, algebra. Okay. All right. Here's a new one. We didn't write this down previously, but this is also very important. The magnitude of the cross product. Turns out there's geometric significance to the magnitude of the cross product. It's the area of the parallelogram defined by those two vectors. Isn't that weird? By the way, let me draw your attention to this notation here. I may have created that notation. I'm not sure. It seems like a natural choice, and it's all so common that I need to refer to a parallelogram defined by two vectors. And, parallelogram's a long word. There's a lot of letters, right? And it's just very handy to put two parallel lines and followed by a list of two vectors. And the interpretation should be this is shorthand representing that parallelogram defined by those vectors. So you'll see that a lot going forward. And if I list three vectors, that means parallelepiped. Pretty natural, I think. Okay. All right. Okay, so that said, the magnitude of the cross product is the area of the parallelogram. Very, very, very far from obvious. Why is this true? By the way, the book gives a proof of this. As I recall, the book does it in a way that uses lots of trig. And that's fine. I mean, it gets the job done, and it's true. But I think it's, again, sort of unsatisfying. It's also seemingly way too much trouble. And furthermore, as it turns out, it's completely unnecessary. I'm going to show you a proof of this fact here that uses no trig at all. None. And I find that very satisfying, right? To be able to avoid. Why do trig when you don't need to do trig? It's just, by the way, it's also a tedious use of trig. It's not clever and simple. Okay, so here we go. This is another mathematical bank shot. These are the two objects that I'm interested in, and I'm going to show that these two things relate to each other by computing this thing over here. Right? I'm going to get here by going that way. And so it's like. But by the way, does everybody get my reference when I say a bank shot? I sort of, maybe I shouldn't assume that everybody knows billiards and pool. Right? But on a pool table, right, with the balls and the bouncing off the edges and the pockets and stuff, right? Okay. If you want to get a ball that's here into a pocket that's there, sometimes, depending on the circumstance, you knock the ball and bounce it off the edge, and then it bounces into the hole. And so they call this a bank shot. Sorry if that was too obscure of a reference previously. Okay, so mathematical bank shot. I'm going to compute these two things by considering instead a third, seemingly unrelated object. And here we go. For no apparent reason, let's compute this determinant. First observation, determinants are triple products. That says determinant is a triple product. If you don't believe me, look at this. First row, dot, second row, cross, third row. I mean, it's literally a triple product. Determinants are triple products. Okay, well, and now having written down that determinants are triple products, notice that as it turns out, I did this on purpose, by the way, but coincidentally, I have a vector dot itself, and vector dot itself is a magnitude squared. Okay. So, by the way, while I'm here, let me observe very quickly and easily. Note, squares, never negative. Handy. Okay. Okay. Now, what does this tell me? Nothing. So, next step. I need to consider this exact same thing again. I'm going to compute this same thing now a different way. And that is going to be done by recalling that determinants are volumes. A determinant is the volume of the corresponding parallelepiped. Oh, wait, absolute value. Oh, no problem. I don't have to say absolute value. I already know that this thing here is not negative. So I can ignore the absolute values that I otherwise would have to stick in there. Okay. All right. Okay, so this volume. Now, let's see here. This volume, well, I'm going to compute that volume. Let's write down the three vectors that I have. There's V, and then there's W. And the third vector, you'll notice, is V cross W. Well, again, that's what we're faced with. And recall that we already know that cross products are perpendicular to the two input vectors. So this is not just a random parallelepiped. This is at least a partially right parallelepiped, right? This direction is perpendicular to the other two directions. And so because of that, I can rewrite this volume that I've got here. Keep in mind I'm interested in that volume. Volume is equal to that distance, which is the magnitude of the cross product, times this area down here, because of those right angles. Everybody remember their high school geometry about okay. Yeah. Okay, so let me remind you what I have done here in my attempt to understand this equation. I have computed something totally different twice. Right? Not clear how that's helpful, but here's the thing. If you compute something twice, your two results have to equal to each other. And if you take these two, now we know equal results, and cancel a common factor of magnitude, notice that what comes out is that. So, that fact, cancel a common factor of magnitude, and we get what we want. So it's a real slick little proof. By the way, I want to emphasize this is very much a slick and clever proof. I am not suggesting that you should have been able to come up with this idea, this clever move here on your own. Absolutely not. No, that was a really, really tricky move that I pulled, right? And honestly, I probably got showed this at some point years and years ago, and maybe I forgot or something. But anyway, it's a very clever move. That said, even though I don't expect that you would have come up with this argument on your own, you don't have to. I showed it to you, right? So it's one thing to have been able to come up with it on your own. It's a very different thing to remember what the trick is and to be able to, and to understand the steps in the argument. That's what I want you to get out of this, is to follow the individual the steps and see how these ideas, and again, notice how many ideas have kind of come together in this one argument to give us an answer. Notice how they all kind of fit together. Yeah?
Are you allowed to reference that you know what volume equals though?
I don't understand. Sorry.
Is the volume formula
Yeah, no, you're quite right. I mean, so I never did prove this claim here, right? So, and I confessed to that at the time. I'm just not going to prove that, and that's going to make everything that follows not, in fact, rigorous. Granted, right? So I confessed to that earlier, and look, we can make it rigorous if you want, but it's just that it's a deeper argument, and it's in a class like Math 212. I think it's very appropriate in a circumstance like this to say, trust me. No, good catch. Absolutely. Yep. So what you've pointed out is going to be a weakness in a lot of the stuff that we're going to do in this section, but it's a weakness of rigor that you're not responsible for. So I'm going to say no problem. Yeah. Okay. Cool. Yeah. All right. So neat fact: magnitude of a cross product is an area. And this gives us a nice foot in the door to understanding. And again, this can be proved algebraically, right? So I don't want to address the question of, is this true? I want to address the question of, should this be true? Why? What's going to make me feel like this ought to be true? And the satisfaction there is that this, I'm going to say coincidence in the sense that whenever one of these true, the other one's true. Seemingly not obvious, but notice both of these facts are easily relatable to the area of the parallelogram being zero, right? This right here, if the length of the cross product is zero, well, the area is zero. That's what this formula right here says. We just proved it. Geometrically satisfying, right? And why should these be simultaneous? Well, again, geometric appeal. think about a parallelogram, and how are you going to make a parallelogram with area 0 without having the vectors be parallel or one of them be 0? So this is just, I think, again, real geometric satisfaction, really geometrically sort of natural and easy to see. So this fact gives us a natural intuition for why this ought to be true. Okay. All right. Okay, so we have what I'm going to call an almost complete geometric description of the cross product. The cross product, given a couple of vectors, well, it's got a point perpendicular to the two vectors, and this area tells us the magnitude, which means my magnitude has got to be, well, it's got to be that distance. But note that does leave sort of two possibilities. I mean, maybe the cross product is that way, maybe the cross product is that way. Which way, in fact, does the cross product point? Knowing it's perpendicular doesn't reduce down these two possibilities. So which one is it? This is actually a quite an easy matter to settle, and that is we've already kind of addressed this determinant is a triple product, which is therefore a self-dot product, which is therefore a magnitude squared, which is therefore positive. So we already know that is a right-hand order. And if that's a right-hand order, then geometric appeal, this argument again. If that's a right-hand order, then that's a right-hand order. And this is the way people tend to think about it. This is what a lot of people call the right-hand rule of cross products. If you want to know which way does the cross product point, index finger in the direction of the first vector you're crossing. Notice. Middle finger in the direction of the second vector that you're crossing. And then your thumb is going to point in the direction that the cross product points. Right? So that right-hand rule comes from the fact that we see that this is a right-hand order, which comes from the fact that we've already established this equation right here. Okay. All right. Okay, so there's so much geometry, there's so much connection between different ideas in this section. It's really kind of beautiful how this everything kind of fits together. It's like all the puzzle pieces kind of it's really natural. So a bunch of neat facts about it, and they come together to give us this now complete geometric characterization of the cross product. By the way, we could have. It wouldn't have made sense at the time, but we could have started our discussion of cross product with the following as a definition. That the cross product of two vectors is the unique vector that has these three properties. Right? That's got to be perpendicular to two input vectors, following the right-hand rule, and with magnitude equal to the area of the parallelogram. That is a well-defined definition. It seems super arbitrary, though. But then from this definition, we could go back and we could derive the algebraic formula and prove by adapted arguments accordingly all of the properties that we've just seen. Okay. All right. So I like to do it. I think it makes more sense to start with the formula and do it this way. But that's it's optional. Okay, but I think it's important to understand that we have this geometric characterization of the cross product. Make sure to understand that it's the unique vector that has these three properties. Okay. All right. This next page, there's one thing on this next page that I want to talk about. Everything else is kind of, you could read on your own. But I promise I'd give you some sense for why the cross product is anti-commutative, right? It's not commutative. But it's more than just not commutative. It's weirder than that. It is explicitly exactly anti-commutative. And there's a real easy demo of why that ought to be the case. If you have two vectors, V and W, well, there's V cross W. There's W cross V. I mean, you can just do this with your hand. I mean, same two vectors, V and W. Just if you want to list one first and then the other first, notice you're just turning your hand upside down. So of course your thumb goes in the exact negative direction with the exact same parallelogram and therefore the exact same magnitude, and therefore those two cross products are negatives of each other. Just like that. Very satisfying. Okay. I'm going to let y'all read the rest of this page yourself, if you like. It's not actually important. You can also skip it if you like. Okay, so moving on now to the next section, lines and planes. See how far we can get in here. First thing I want to talk about is we're going to talk about the equation of a line, equation of a plane. And I want to make sure we're all on board with the right point of view on what that means when we say the equation of a shape. You know, is it just algebra that you write down? Importantly, no, it's more than that. It's not just algebra that you write down that relates in some way flexibly to the shape that you're talking about. An equation of a shape is a test. Very importantly, it's a test. If you have a point, if it satisfies the test, then it is on the shape. And if it does not satisfy the test, if it fails the test, if it doesn't satisfy the equation, then it's not on the shape. So it's literally a test. And that's a great way to think about it, and I want to encourage everybody, when you hear the phrase equation of a whatever, think in those terms. Okay, so I want to talk about the equation of lines in R2. Y'all remember the equations of lines in R2. Yawn, right? What's that, 6th grade, 7th grade? I don't know. It's a long time ago, whatever it is. But I want to talk instead about a different way to think about it. You'll see why in a couple moments. Let's consider a scenario where I am given a point and I'm given a vector, and I would like to find the equation. There's that term. I want to find the equation of the unique line that goes through that point and that is perpendicular to that vector. So, weird question, right? But let's play my game, right? So, you got to grant me, if I give you a non-zero vector in and some other point x naught, that there is in fact a unique line that goes through x naught and is perpendicular to n. Okay, and how would we test a point x, x comma y? How would I decide whether that is or is not on said line that I'm trying to understand? Okay, all right, well, it's an easy argument. If the point is on the line, notice that would mean that the difference vector is parallel to the line, which you'll further notice means that it's perpendicular to the in vector. Further notice, if the point were over here, right? If the point were not on the line, then that difference vector would not be parallel to the line, which means that these two vectors would not be perpendicular. And so I can write that down algebraically. Whether or not these two vectors are perpendicular, the perpendicularity of those vectors completely decides for us whether x is or is not on this line. And that's easy to write down algebraically. Here you go. So x is on the line if and only if the difference is parallel to the line, which means that difference is perpendicular to the in vector. Hey, perpendicular means dot product is equal to 0. And by the way, let's pay more attention to some details. This in vector that I defined here, that in, let's give it coordinates a and b, whatever. Let's call them a and b. This x naught vector here, let's just put down some stuff. We're going to call it x naught comma y naught. Right? And having done that, notice that this dot product, which, by the way, notice you can distribute. Right? This dot product here becomes ax plus by. And this dot product over here, in and x naught are both given, so they're crank out that dot product. It's some number, whatever. Let's just call it c. And lo and behold, what we get then is, the old equation for a line, which, again, we all know, that's old news, ax plus by equals c. What is new, what you've probably not seen before, certainly you didn't see, well, certainly I didn't see the following when I was in, middle school or whenever you learn this stuff, is what these things mean. What are the A, the B, and the C geometrically? I was never given any answer to that. I never liked this equation when I was in high school, middle school, what have you. I liked this equation because m is the slope. I can see that. That's geometrically satisfying. M means something. K is the y-intercept. That means something. I can see it. It's geometrically natural. So that was a geometrically satisfying way to think of lines way back when. But here's the thing. Now, this is a geometrically satisfying way to think of lines because these numbers A and B, those are this in vector. That's a vector perpendicular to the line. They never told me that in high school. Well, they could, in their defense, they couldn't. We didn't know dot products, right? We just didn't have the tools. But I think that's really, really interesting that the coefficients in the equation of a line tell you something geometrically natural about the line. And then, by the way, the exact same argument goes through for a plane in space. If you give me a point and a vector, there is a unique plane that goes through that point and that is perpendicular to that vector. Unique plane. Another point, whether that point is or is not on the plane, is entirely decided upon by whether that difference vector is parallel to the plane, aka perpendicular to the in vector. Go through and do the exact same algebra, and look at this. We get the equation of a plane in space. Oh, and I'm out of time. Okay, so we'll call it a day right here. We'll pick up here on Friday. See y'all later. Have a good one.